Okay, are we running? Are we a go? I think we might be running. I think this might be a go. Okay. Hello, good people. I have something here to show you. Okay. 1 second. Okay, so here's what I have. I have this battery. This battery is connected to a, or I should say, I have this battery here that's then connected to this wire. This wire is connected down to this little very, very thin copper wire. This copper wire is going between the two bars of this horseshoe magnet here. This magnet has a north pole and a south pole, and now's the part where I need to remember which is which. Yes, that's right. The one that's far away from me, closer to you, this is the north pole of the magnet, and the one that's closer to me here, this is the south pole of the magnet. Now, the wire is connected to the positive terminal of the battery on this end. And then this wire is connected to the negative terminal of the battery on this end. And the negative terminal of the battery is connected to a switch here. Now here's what I'm going to do is I'm going to go ahead and flip this switch. And when I do, I want you to watch what happens to this little wire here. We'll see if you can see it. It's kind of a, you're looking at a very small wire on a very grainy computer screen, but we'll see how it goes. Okay, here we go. Ready? Do you see it? I'll do it again. Here we go, flipping the switch, and now. What you should see is that when I flip the switch, this little wire, whoop, jumps up in between the bars of the magnet. Now check this out. Here's what I'm going to do now is I'm going to take these two terminals and I'm just going to flip-flop them. So now this end of the wire is connected to the negative terminal of the battery, and this end of the wire over here is connected to the positive terminal of the battery. I'm going to do the same thing. I'm going to flip the switch. Are you ready? Watch very carefully, see if you can see it. Do you see it? I'll do it again. There it is. Lots of interesting stuff going on here. It appears that this magnet shoves the wire when the wire has a current going through it. Any thoughts on why that might be? Well, here's what I'm thinking. I know that a magnet creates a magnetic field, and I also know that a current-carrying wire creates a magnetic field. And if the wire, when it has current in it, is creating a magnetic field, and the magnet is creating a magnetic field, we know that magnets shove on other magnets. And so this magnet is going to shove on the little wire just like it would shove on a little magnet, and the little wire moves. Today, we're going to talk about forces on charges that are moving in magnetic fields and forces on current-carrying wires that are in an external magnetic field. So far, in this unit, we've talked about permanent magnets, and then we've talked about the first right-hand rule, and we've talked about magnetic fields created by current-carrying wires. Well, now we're going to enter into kind of a new topic. There are really 4 topics in this unit. The first topic is permanent magnetism. That's like if you have a bar magnet and then it's just creating a magnetic field. The second topic is magnetism that's created not by bar magnets, but magnetism that's created by wires or by moving charges. That's something that we already talked about when we talked about the right-hand rule and when we talked about the Ampere's law. Now, what we're going to talk about next, our next topic, is forces on charges that are moving in B fields. The previous 2 topics, we've been looking at how a magnet or how a wire can create a magnetic field. In the next topic, we're going to talk about how do moving charges respond to that magnetic field. How are moving charges influenced by the magnetic field? Today, we're going to learn a new right-hand rule that shows us the direction that a charge will move when it's exposed, that a moving charge will move, or that a moving charge will accelerate, when it is exposed to a magnetic field. And then we're going to learn an equation or 2 that teaches us about the magnitude of the force on a moving charge in a magnetic field. So once again, to recap, everything that we've done so far has been about creating magnetic fields, either from a permanent magnet or a wire. What we're going to do starting now is how things respond to magnetic fields. How does a wire respond when it's in the presence of a magnetic field? How does a little moving charge respond when it's in the presence of a magnetic field? Today we're talking forces on charges that are moving in magnetic fields. And I'm going to go ahead and pause the video and get us resituated here. No, I can do it. I can do it, I swear. Okay, we are situated here and ready to go. Today we're talking about forces on charges that are moving in magnetic fields. Now, here's the idea. If you have a little charge that is moving, and that moving charge enters a magnetic field, well, that moving charge is creating its own magnetic field. And so you'll have an interaction between the external magnetic field and the magnetic field created by the little charge that enters the magnetic field. Those two will interact and it'll create a force on that moving charge. We're going to talk about three topics today. We're going to talk about 3 topics today. First, we're going to talk about how do you determine the direction of the force on a moving charge. Then we'll talk about how do you determine the magnitude of the force on a moving charge in a magnetic field. And last, we'll talk about how do you determine the magnitude of the force on a current-carrying wire in a magnetic field, something like we just saw in our demo. To start, we're going to talk about how do you determine the direction of the force on a charge that enters into a magnetic field. You have already learned one right-hand rule. Well, now it's time to learn a second right-hand rule. This is what I like to call right-hand rule number 2, and I call the other right-hand rule number 1. Right-hand rule number 1, you'll remember. Sorry, I'm going to make this big. Right-hand rule number 1, you remember, you use right-hand rule number 1 to find the direction of the magnetic field created by a current-carrying wire. What you do is you point your thumb in the direction of the current and your fingers will curl around the wire in the direction of the magnetic field. We use right-hand rule number 2 to figure out which way the force will go on a moving charge that enters into an already pre-existing magnetic field. Here's the difference, and students will mix up their right-hand rules and use the wrong one all the time. So make sure that you know when to use each one. The first one, right-hand rule number 1, is for finding the direction of the magnetic field created by a current-carrying wire. For finding the direction of the magnetic field that's created by a current-carrying wire. The second right-hand rule is for finding out the effect of a magnetic field that's already there. It's for finding out the effect of a magnetic field that's already there. So right-hand rule number 1 determines the direction of a magnetic field that is being created. Right-hand rule number 2 determines the effect of a magnetic field that's already there. To do right-hand rule number 2, you raise your right hand like this. Your right hand should be, unlike last time in right-hand rule number 1, it's a nice curly right-hand rule. No such thing as curls in this one. You have a nice flat hand like this. Your thumb is going to point in the direction of the moving charge. Your thumb will point in the direction of the moving charge. And your fingers will point in the direction of the magnetic field. Again, this is different because this is the magnetic field that's already external, not the magnetic field that this little charge is creating. So you're going to have your thumb points in the direction of the moving charge. Your fingers point in the direction of the B field. And finally, your palm will show which way the force on a positive charge will go. A negative charge will get shoved the opposite direction. So we'll try a practice problem here in a second where you get to see that. Okay, let's go ahead and try a practice problem here. Suppose that you had an external magnetic field that was going into the screen like this. So maybe there's another magnet in here, maybe there's something happening, maybe there's like a north out here and there's a south back behind the screen, but for some reason there's a magnetic field that's going into the screen. Now, let's suppose that a little positive charge happened to wander into this little field. Actually, I'm going to draw it in a different color. If a little positive charge happened to wander into this field, and the little positive charge was moving. Well, a moving positive charge would create a magnetic field. And the magnetic field from that moving positive charge would interact with the magnetic field around it. So, wait, hang on. Come on, team. Why are we not working? Oh my, you could do it. You can do it. Everybody just got to load for a second. Oh my. Erase. Beep, doop, doop. Okay. Let's say that we had a little positive charge right here. That little positive charge is moving this way. And that little positive charge, because it's a charge and because it's moving, it's creating a magnetic field. And the magnetic field of that thing is going to interact with the magnetic field around it. So I have a magnetic field that has a strength, we'll call it B, and a direction that's going into the board. This little particle has a speed of V. Let's talk about which way it would go. I use my right hand rule. Now, as I learned in the last video, it's nearly impossible for me to kind of try to watch myself on the screen and still get it right. So what I'm going to do is I'm just going to do it the way that I see it. You do it the way that you see it, okay? So you might have to do what is mirroring me because I'm just doing what I see here. Here's what I see. I see that the direction that the charge is moving is to the right. So I point my thumb to the right. Then I point my fingers in the direction of the magnetic field. The direction of the magnetic field is into the screen, like this. My palm then shows the way that a little positive charge would get shoved in this field. And because my thumb points to the right, my fingers point into the screen, my palm is facing up. So this little positive charge would get shoved up like this. And that is the direction of the force on the charge. Let's try another practice problem. I'm going to shrink this down here. Let's go ahead and make another magnetic field here. Let's say this time we have a magnetic field. Oh gosh, not like that. No need to be dramatic. Okay. Let's say that we had a magnetic field that this time is coming out of the screen towards you. Like this. And let's say that we have a little positive charge. It goes wandering in, and this positive charge is going up like this. That's the direction of the positive charge. Let's figure out which way the force would be going on this little positive charge. I point my thumb in the direction, I'll draw this big, or I'll make this bigger so you can see it. I point my thumb in the direction that the positive charge is going, so it is going up. I point my fingers in the direction of the magnetic field. When I'm looking at this, the magnetic field is coming out towards me. So I'm going to point my fingers back towards myself. Now the palm of my hand here shows the direction of the force on a positive charge. So this charge is going to get shoved to my right, this way. So I'm going to write that the direction of the force on this charge is to the right. And that's how it'll get shoved. Let's try another one. Let's do a magnetic field that looks like this. This time it's going back into the screen. And then let's say that I had a little electron here, and that little electron was moving this way at a speed v. When you use your right hand rule, the palm of your hand represents the direction of the force on a positive charge. But that's going to be the opposite as the direction of the force on a negative charge. So I use the palm of my hand to show which way a positive charge would get shoved, and I use the back of my hand to show which way a negative charge would get shoved. I always slap the face of positive charges and back slap the face of negative charges. So here's what I do. First, I point my fingers in the direction of the magnetic field that is into the screen. Then I'm going to point my thumb the way that I see the little charge moving, which for me is to the right, so I point my thumb to the right. The back of my palm then shows me which way this little charge is going to get shoved, and it's going to get shoved down, just like this. So I'm going to show F going down, like that. Last one of these ones, and then we'll try some more for you to try. Let's say that I had a magnetic field going like this, and then I had a little negative charge here. And that little negative charge is going down. So this is the direction of my magnetic field, and this is the direction of the negative charge. Which way would this thing get shoved? Well, let's try it. We point our fingers in the direction of the magnetic field. our thumb points in the direction that the charge is going. So my fingers are going to point to my right. My thumb is going to point down. Back of my hand shows me where that thing is going to get shoved, and it's going to get shoved back into the screen. So I'm going to write a little X to show that that little negative charge is going to get shoved away from me like that. Now let's try another one. All of these so far have used a single charge that's moving in a magnetic field. But you could also have a wire that's moving in a magnetic field. And by moving, I mean the charges inside the wire are moving in the magnetic field, and then the magnetic field moves the wire. Let me show you what I mean. Let's try one like this. Say that I had a magnetic field that was coming out of the screen. And I had a little wire here. And that little, whoa, golly gosh, goodness. Let's draw that perpendicular, shall we? Still not quite perpendicular. Let's try one more time. And then I give up. Okay, I give up, fine. You know it's perpendicular. We'll attach this end to the positive terminal of battery. We'll attach this end to the negative terminal of battery. Hey, that means that we have charges that are flowing in this wire. We know that the negative charges are going down. The direction of the current is up the wire. This little wire that's in a magnetic field will get shoved just like the little wire that we saw in our demo earlier. So here's how I figure out which way it's going to get shoved. My fingers point in the direction of the magnetic field, and my thumb this time is going to point in the direction of the current, because that's the way that we would say positive charges are moving. So I'm going to point my fingers at my face like this. I point my thumb up in the direction of the current. My palm shows me which way a positive charge would get shoved, which works well here because isn't current always the direction of positive charge? So I go like this. My palm shows me which way a positive charge would get shoved, and it looks like it would get shoved for me to the right, like this. You go ahead and try one. Say that we had a magnetic field that looked like this, and say that we had a wire here that was perpendicular, like a nice line there. Okay, we'll put 6 volts over here. We'll put 0 volts over here. Can you find out which way this little wire would get shoved? Take a minute, pause the video, figure it out on your own, then come back. Okay, here's what you did. You said that the direction of the current is going to go from high potential to low potential, so you said this is going to be the direction of the current. Point your thumb in the direction of the current, which is to the right. Your fingers then should point into the screen. Then your palm is now facing up, so this little wire is going to get shoved up, and the force on the wire will be this way. So you can see how you can use right-hand rule number 2 for finding the force on a charge that is moving in a magnetic field, or finding the force on a wire that is carrying current through a magnetic field. Before I move on, can you please stop and tell yourself, remind yourself, make sure that this makes sense to you. When do we use right-hand rule number 1, and when do we use right-hand rule number 2? What's the difference between the two? What are their two purposes? Go ahead and check that with yourself as I go ahead and get a new document pulled up here. Okay, feeling good on the difference between right-hand rule number 1 and right-hand rule number 2? I hope so. Here's what you learned. You learned how to show the direction of the force on a charge that is moving in a magnetic field. But we still don't know exactly how hard the force will be. Will it shove it really gently, or will it shove it really seriously? How hard will the force on the charge be? Well, in order to do that, you would have to find a way to calculate the magnitude of the force. Well, just as a reminder, we already know a few things. Here are some things that we already know. We already know that the strength of the gravitational field is equal to Fg over m. You also already know that the strength of the electric field is equal to Fe over Q. In other words, the electric force divided by charge. And lastly, you know that the size of the magnetic force is equal to the strength of the magnetic field is equal to the magnetic force divided by a moving charge, which we represent by Q for charge and V for moving. If you wanted to find the force on a charge that is moving in a magnetic field, you would just have to rearrange this equation. And you would rearrange it to say that the force on a charge that is moving in a magnetic field is FB equals charge moving in magnetic field QVB. And that equation is worthy of your bag of tricks. quick little side note here on this equation, you'll see that FB is equal to QVB. Notice that it doesn't have any vectors right now. That's because that this actually is a, like deep down, we actually have a cross product situation going on here. So that's where you can have vector hats. Basically, this cross product just means that the direction of the force is perpendicular to the direction of the motion and the direction of the magnetic field. That is something that you already take care of with your right-hand rule. So in my class, as long as you have the direction taken care of with the right-hand rule, then you can pretty much just ignore this equation and you can ignore direction in your equation, and in your equation we just use this to find the magnitude. This equation should make some amount of sense to you because when you look at it, you see that FB is equal to QVB. Well, that's the force on a charge that is moving in a B field, where Q is the charge, V is the speed of the charge, and B is the strength of the magnetic field. Don't you see that the force on a charge moving in a B field relies on all the things you would think it would rely on, basically charge and movement and B field? If you have a bigger charge, or if that charge is moving faster, that moving charge is creating a bigger magnetic field. And if it's creating a bigger magnetic field, the force on it will be greater. Then here you have the strength of the magnetic field. If the strength of the magnetic field increases, then it's going to shove on that little charge harder. I also like to say that this is reminiscent of one of my favorite songs from one of my favorite movies, when Julie Andrews in The Sound of Music is talking to all the children, and all the children are very scared because there's a thunderstorm outside, and Julie Andrews says, "Come around, little children, gather on the bed. Whenever you get scared, all you have to do is remember all of your favorite things." And she sings a little song, and she says, "Forces on charges moving in B fields. These are a few of my favorite things." Yes, isn't that what she says? So this is actually how I always remember this equation, is I don't remember F equals QVB. What I remember is forces on charges moving in B fields. And that's how I remember the equation every single time. This is the equation that works for a charge that is moving in a magnetic field. But we also would need a different equation if we wanted to know the force on a current carrying wire. Here's how we would do that one. Check it out. We know that FB is equal to QVB, where Q is the size of the charge, V is the speed of the charges in the wire, and B is the direction of the magnetic field. Well, the speed of the charges would just be the distance the charges travel divided by the time that it takes them to get there. Well, hey, here's something that we know. We know that if you take a certain amount of charge, and you divide it by a certain amount of time, that gives you the current. Q over delta T is current. X, that's the distance the charges travel. In this case, that's going to be the length of the wire that's in the magnetic field. And finally, we write B for the strength of the magnetic field. And this equation gives you the force on a wire that is in a magnetic field. Now this one has a nice little song to go with it. This one I actually don't have a song for, and I have always just remembered this as I love bagels, which has literally zero to do with anything, but that's just how I've remembered it my whole life. Once again, note on this equation, it's actually ILB with a little cross product. Here is the truth with little vector hats on these things, and then a little vector hat on this thing. But we won't deal much with vector hats. If you have a cross product here, sometimes you'll reduce that down to this, where you say ILB times sine of theta, where theta here is the angle between the wire and the magnetic field. So sometimes if you have a wire going this way and a magnetic field going this way, then you'll use that cross product to figure out the sine, or you'll use the sine of theta to figure out the angle between them. But you don't really need to know much about that for this class. Just a little sneaky side note for you. Hey, before we try some practice problems first, can you please tell yourself, make sure that you understand, what's the difference between this equation and this equation? When do we use each one? And as you're working on that, I'm going to go ahead and get a new page pulled up here. Okay, the first problem that we are going to try is going to be a mass spectrometer problem, and it is going to introduce you to both new technologies and remind you of pretty much everything we've been doing this whole year. So to get started, I'm going to draw you a picture of a mass spectrometer. Here we go. We got one plate right here. Oop, that's a little crooked, but it's okay. We're going with it. We're totally just going with it. It's awesome. One line here, like this. This is gonna be a metal plate that has a positive charge on it here. And then this is going to be a metal plate that has a negative charge on it here. And then out here we're going to have a nice magnetic field. Let's say that that magnetic field is directed into the screen like this. Okay, now here's the vision. If we want to find out the mass of a proton or an electron, I'll tell you what we don't do. What we don't do is we don't take out a little scale and put a little electron or put a little proton on top of a scale and see how much it weighs. That's not how we do it. If we want to find the mass of a proton, we need a special device called a mass spectrometer, and it looks something like this. You have the speed chamber is what I'll call it, which is these two plates right here. You have one that's positively charged, one that's negatively charged, and then you have this magnetic field here. Here's how it works. You put a little positive charge. Oh, I'm actually going to change my color now so that you can see it distinct from the other colors. 1 second. Here we go. Okay. Here's what you're going to do. If you want to find the mass of a charge, what you'll do is you'll take that little charge here and you'll put a little positive charge, the one that you want to find the mass of, right next to the plate that it hates. So you put the little positive charge right next to the positive plate. When you do that, that little positive charge does not feel very happy where it is. And so this little positive charge will start to accelerate towards the negative plate. Because here we have a difference in potential. And you know, whoa, that was crazy times. Here we have a difference in potential. Why can I not make a curvy thing? Here we have a difference in potential. And as you know, a potential difference is what makes charges go. Here it has a lot of potential energy. Over here it has less potential energy, but lots of kinetic energy. When it gets to right here, that charge is moving very, very fast, but it doesn't actually stop here because there's a little gap in the plates here that lets this little thing go through. Now it's going so fast that it's not going to stop here. It's actually going to keep on going straight and enter into this magnetic field. And then some interesting things are going to happen to it. When it enters into this magnetic field, let's talk about the force that this little charge is going to experience. I want you to imagine that this magnetic field here goes like all the way right up next to this plate. So here's your magnetic field. Well, here's what's going to happen. This little positive charge enters into this magnetic field and it's going to experience a force. Can you use your right hand rule to figure out which way that force is going to go? I bet you could. Go ahead and try it. Here's what you say. You say, okay, well, it's going this way. So I'm going to point my thumb to the right. My fingers are going into the screen, and then my palm is pushing up. So this little thing is going to experience a force directed upwards like this. That is absolutely true. But here's what I want you to imagine. This thing is not going to go, get into the magnetic field, stop, and then say, oh, I should be going up, and then zoom straight up. That's not what's going to happen. It's not going to go, that's not the process. What it's going to look like instead, because it has inertia going this way, is that it's going to slowly get pushed up, but its inertia is going to keep it going forward, and so it's going to curve. Now, eventually, as this curves around, it's going to get to a spot, let's call it right here, along this nice curved path here. Right here, at this point, now this little particle is traveling up and its speed is up. But now, check it out, the force is going to be in a different direction. Can you find out which way the force is going to be? Use your right hand rule. I'm going to clean things up a little bit here so that you can see a little bit easier. Okay, you pointed your thumb the way that this charge was going. You said it was going up. You pointed your fingers in the direction of the magnetic field. You said that it's going into the screen. And your palm will shove this thing to the left. So the force on this little charge now will be to the left, like this. Here is the force. Now, here's what's not going to happen. It's not going to be on its way up, stop dead in its tracks, and turn around and go left. That's not what's going to happen. It's actually going to gradually keep going up, but generally trend towards left until it lands at a spot on the plates all the way up here. When it lands at the spot on that little negative plate all the way up here, it will actually be going this way. Now, if there wasn't a plate here to stop it, if it could keep on going this way, you see that this little charge would keep going in a circle. The force would be constantly directed towards the center of the circle, and the little charge would be constantly moving. However, because there's a plate that gets in the way, it's only going to make a little bit of a circle. It's only going to go half a circle, a little semicircle. And so, let me get this out of the way. Sorry, negative charges. Boop, 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 boop. Bye, you're not important anymore. I don't mean that. You always matter, but just not for what we're doing right now. Okay, so then what this mass spectrometer has is it has a little detector right here that detects where exactly this little positive charge lands. And because it can detect where exactly this little positive charge lands, it can detect, wait, let me try this again. It can detect the radius of the circle. I'm going to make that a lowercase r, sorry T. It can detect the radius of the circle that the little positive charge is going in. We can use the radius of this circle to figure out the mass of the positive charge. Let me show you how. I'm going to erase some of our magnetic field here, but of course you know it's there. Once again, I just need a little more space to write. Let's say, and I'm going to do all of this algebraically here, but you could also totally plug in numbers here and get to final answers. But I'm just going to show you a little bit of an algebraic example. Sorry, this is obnoxious as I take like 5 years to erase all the little tiny little guys that are just kind of hanging out. Okay. Here's what we're going to do. You can see that the first part of this mass spectrometer, the whole point of this part of it is really just to launch the little charge over here. So before we even get to this magnetic field part, let's see if we can't figure out how fast this charge is going after it makes it through this far. In order to do it, you would have to know something about this little particle, namely you would need to know its speed, you would need to know its charge Q in order to find its speed. Sorry, let's get rid of that real quick. Bye. Go away, please. Go away, please. It's working. Just gonna take its time. We're just gonna let it take its time. Or maybe I get impatient. Oh geez, okay, just let it take its time. Nope, my impatience is winning. Come on, buddy, you can do it. You got it, internet. Go, internet, go. Okay, let me see if I can't pause this while it waits to load. Okay, so for some reason my undo button is just super not working right now, but that's okay, we will make do. Okay, so this is going to be my charge right here. I have to know the size of the charge here in order to figure out how fast it's going. Let's go ahead and see if we can't figure it out. Here's the idea. When it starts over here, it has tons of potential energy. When it ends over here, it's going to have a lot of kinetic energy, and it's going to trade its potential energy for kinetic energy. So to find out how fast it's going, I can use conservation of energy. Here's how we do that. We say the change in electric potential energy plus the change in kinetic energy together is going to equal 0. For my change in electric potential energy, you'll recall that delta V is equal to my change in potential energy divided by Q, because electric potential difference is like the difference in potential energy, but just without the charge there to feel it. That means then that my change in potential energy is equal to my delta V times Q. So I can plug in over here delta V times Q, where delta V is the difference in potential between these two places, and Q is the size of my charge here. We can add that to delta K, which is going to be a K final minus a K initial. If I start this little guy at rest here before I let him go, then this K initial will be equal to 0. So then I get an equation that looks like this. I got a delta VQ. You'll recall that the equation for kinetic energy looks like 1/2 mv final squared. And that's going to equal 0. Now at this point, I could rearrange and solve for V final. And I would get something like this. I'd get that V final. Notice here, this should be a lowercase v. This is a capital V. You can draw little hats on your capital V if you want to make sure that it looks distinct from your lowercase v. So then V final is equal to 2 times delta VQ. When we rearrange, it's 2 times delta VQ divided by m square root of that whole thing. Now that was a quick rearrange, so if you need more algebraic steps, then take more algebraic steps, but that's where you land. So that gives us how fast it's going when it gets right here. Now let's see how knowing the radius could help us find the mass of this little thing. Here's the idea. Once it gets into this magnetic field, do you see that it's constantly going in a direction that's perpendicular to the force, and the force is constantly pulling it back towards the center of the circle all the way around? That means that our force is acting as a centripetal force because it's making this little charge go in a circle. So we say here that FB, our magnetic force, is a centripetal force. You know an equation for FB because we just learned it. The force on a charge that is moving in a B field is a charge moving in a B field. Where here you do have to know that B is the strength of the magnetic field that we created for the mass spectrometer. Then the centripetal force is, wow, that was a crazy, that's a crazy equal sign. The centripetal force, you'll remember, is equal to mv squared over r. Hey, check it out. You'll notice that one of these v's cancels out. And if you rearrange and solve for r, you'll see that r is equal to mv over qb. Now here's the cool news, is that we actually already found an expression for v, because the v here is equal to the v that was the v final for this little portion here. So your v is equal to m, then we got the square root of 2 delta VQ all over m like this, divided by QB. If you look at this equation here, do you see how if you knew R, you could rearrange here and find the mass of this little proton? If you had a mass spectrometer set up, you would be able to control the delta V and the B. So you'd set your delta V, you'd set your B, you'd know the charge of the particle that you're testing, and you could use this to find the mass. Isn't that pretty cool stuff? And that's how we do it in real life. So this example shows you a little bit about a mass spectrometer, but it also reveals a lot of things and ties a lot of things together. You see that we use conservation of energy, and we use centripetal force, and we use this new equation that you just learned, that FB is equal to QBB. We also see that the direction of the force causes charges to go in a circle. And actually, that'll be true most of the time. Most of the time, you're going to get charges that when they enter into a magnetic field with speed v, where the direction of the velocity is perpendicular to the direction of the field, they will end up going in circles around that field. Very interesting stuff. Now, let's try one more practice problem. This is our last practice problem for today, and this practice problem is related to the equation that we use for the force on a current carrying wire. And we'll get things loaded up here. Okay, let's go purple. We're going to try getting started on page, let's see what this is. This is page 692, number 1. I'll grab my textbook and take a look. You grab your textbook and take a look. We won't walk through the whole problem here, but we will get it started. If you take a look at page 692, you'll see it says number 1 in the purple box. It says a 6-meter wire carries a current of 7 amps towards the positive x direction. A magnetic force of 7 times 10 to the negative 6 newtons acts on the wire in the negative y direction. Find the magnitude and the direction of the magnetic field producing the force. Anytime we do one of these kinds of problems, we will always be drawing a diagram. Let's draw a diagram of the setup. We have a wire that is carrying a current towards the x direction. So I'm going to draw a wire here that is situated in the x direction, and it says it's towards the positive x direction. So that says to me that the current is going this way. I'm going to label that current here. I'm going to say that the current in the wire is equal to 7.0 amps. Okay. Then it says a magnetic force of 7.0 times 10 to the negative 6 newtons acts on the wire in the negative y direction. So I'm going to draw that here. The force is acting in the negative y direction, and that force has a magnitude of 7.0 times 10 to the, oh gosh, I wrote that very bad. Let me use my eraser here. Since my undo button is out of commission. Okay, let's try this. The force, I'll call this FB since it is a magnetic force. The force is equal to 7.0 times 10 to the negative 6 newtons in the negative y direction. And we are looking for the magnitude and the direction of the B field. Well, first, I'm going to find the direction using the right-hand rule. Here's what I do. I point my thumb in the direction of the current. I know that the palm of my hand is going to show me which way a wire gets shoved. So I have to turn the palm of my hand down since this wire is getting shoved down. That leaves my fingers pointing at my face, which says to me that this magnetic field is coming out of the page in the positive Z direction. So I'm going to draw a magnetic field here that is coming out of the page at, oh gosh, wait, not that. Oh, now I have to use my eraser because I can't use my undo button. Okay, sorry team, sorry. Wow, okay, wow, I actually erased that so well. Wow, go me, okay. So I'm going to show that this magnetic field is coming out of the page like this. Whoa, pretend I did those dots evenly, not all like scattered all over the place. Okay. So I have that done. I know the direction now is going to be out of the page. The next step is to find the strength of the magnetic field. To do it, I'm going to use an equation that I just learned. I'm going to use the equation for the force of a current on a current carrying wire of a certain length in a magnetic field. Here's how I'm going to do it. I'm going to rearrange to solve for B here. To rearrange to solve for B, I get that B is equal to force divided by current and length. I know the size of the force, I know the number for the current, and I know the length of the wire because it was given to me in this problem. It says that the wire has a length, oh gosh, I can't believe I forgot to write this in my knowns and unknowns. How embarrassing. Am I right or am I right? It says that this wire has a length here. My length of my wire is 6.0 meters. Wow, that is a very long wire actually. Pretty substantial. Why does that say 7? I don't know, because apparently I'm bad at writing ends. Whoa, that is chalk. Not an eraser. Try again. Okay. Now back in action. Now we could plug in numbers here, get to a final answer, and when you do, once again, we won't walk through this whole thing together, but when you do, you should get something like 1.7 times, wow, I'm writing way off here, times 10 to the negative 7th Teslas. And don't forget, we do need direction in the, I'm going to say, positive z direction. But you could also say out of the page. The reason why I prefer saying positive z direction is because it gave me the directions in terms of positive x and negative y, which makes me think that it wants the final answer in terms of x, y, and z. So that's why that answer is probably preferable. And there you go. And that is all for today, folks. I hope you have a wonderful rest of your day. A quick recap of what we talked about. We did some practice problems here, but actually let's go back and let's run it forward back. We started by talking about forces on charges moving in B fields, and even conceptually why that happens is because each little charge that enters into a magnetic field creates a magnetic field of its own. Those magnetic fields interact with each other, and it creates a force on anything that is a charge that's moving in a magnetic field. So we saw that you can use the right-hand rule. Use right-hand rule number 2 to figure out the direction of the force on a charge that is moving in a magnetic field. Then, after that, we talked a little bit about the magnitude of, wait for it. We talked a little bit about the magnitude of those forces. We said that the magnitude of the force on a charge that is moving in a B field is the charge moving in a B field. Then we talked about how the force on a current-carrying wire in a magnetic field is current times the length of the wire times the strength of the magnetic field. And then finally, we did 2 practice problems. The first one was a really roundabout practice problem with a mass spectrometer. You do need to understand that practice problem, by the way. Hint, hint, nudge, nudge. And then we did another little practice problem where we got started a little bit on one of your homework questions, taking a look at the current in a wire and the force on a wire and finding the strength of the magnetic field. And that's all for today, folks. I hope you have a wonderful, wonderful rest of your day, and I'll see you next time, virtually or otherwise. Bye, good people. Eventually it will end. I just have to really hit the button, like I seriously mean it. You know, maybe we're going to be here for forever.